Sound waves are a fundamental phenomenon in physics that we encounter every single day. They are classified as mechanical pressure waves, which means they require a physical medium to propagate through space. Understanding how sound travels through compressions and rarefactions will help us grasp the true nature of acoustic phenomena. Sound is a mechanical wave, which means it cannot travel through empty space or a vacuum. Unlike electromagnetic waves such as light, sound absolutely requires a medium to propagate. This medium can be a solid, a liquid, or a gas. The molecules in the medium are essential because they carry the sound energy from one location to another through their vibrations and interactions. Sound can travel through solids, liquids, and gases, but it cannot propagate in a vacuum. This is why astronauts in space cannot hear each other without communication devices, even if they are very close together. In outer space, there are no molecules to transmit the sound vibrations, making sound propagation impossible. The presence of matter is absolutely essential for sound to travel. Sound propagates as alternating regions of high and low pressure in the medium. As a sound wave travels, it creates a pattern of pressure variations that move through the material. These pressure changes are what our ears detect and our brains interpret as sound. The alternating nature of these pressure zones is the key characteristic that defines sound as a pressure wave. Compressions are the high-pressure regions in a sound wave. In these areas, particles are pushed close together, creating zones of increased density. When a sound source vibrates forward, it compresses the particles in front of it, squeezing them into a smaller space. This compression increases both the pressure and the density of the medium in that region. Rarefactions are the low-pressure regions in a sound wave. In these areas, particles are spread apart, creating zones of decreased density. When a sound source vibrates backward, it creates space for particles to spread out, reducing the local pressure and density. Rarefactions always follow compressions as the wave propagates through the medium. Sound waves are classified as longitudinal waves because the particles in the medium vibrate parallel to the direction of wave propagation. This means that if the wave is traveling to the right, the particles oscillate back and forth in the same horizontal direction. This is different from transverse waves, where particles move perpendicular to the wave direction. Energy transfers through the medium via particle collisions. As one particle vibrates, it collides with neighboring particles, passing the energy along. However, it is important to understand that the particles themselves oscillate in place, but do not travel with the wave. Only the energy and the wave pattern move through the medium, while individual particles simply vibrate back and forth around their equilibrium positions.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.